Capacitors can be connected in series, in parallel, and many other ways. So let's examine the simpler cases of series and parallel connection. In series connection of capacitors, the capacitors are placed end to end. Now this is a series connection. So this represents two conductors inside the capacitor, and charge can flow into one of the plates and charge can leave the other plate. This is a series connection, number of them placed end to end. Let's consider three of them. Do you realize that there is no flow of charge in the gap? Right? There is a non-conductor there, sometimes a dielectric between the plates, so there is no flow of charge there. This is an end-to-end connection. Well, anything with two ends can be placed end to end. For example, consider some pencils. Say this is the sharpened end, and this is the blunt end, and this is the blunt end, this sharpened end, and we can place them like this. So this is an end-to-end connection, one end touching the other. In fact, in the case of this end-to-end arrangement, we can perhaps reverse this, and then you would say it is improper series if there are two different kinds of ends, blunt end and sharp end, like say in this case. Not in case of capacitors. The two plates, one of them can be positive, the other can be negative, so there is nothing like improper series connection for capacitor. Let the capacitance of the capacitor, first capacitor C1, this is C2, and this is C3. So between these two terminals we have three capacitors in series. If you apply a potential difference by connecting a cell, say this is the higher potential terminal, say let's call that A, and that's the low potential terminal, let's say B. Charge will flow in, and this say would acquire a positive charge. This charge will induce a negative charge here, minus Q, and the induced positive charge flows onto this. This will be plus Q here, and the induced, again negative charge is induced here, minus Q. The induced positive charge flows, and then this would be minus Q, and Q will leave. So Q has entered this terminal and Q has left the terminal B. So connecting a cell causes a charge to be driven this way. Now let's call this C and this D. These are all connected conductors, so they are at the same potential. Again, this. Now we can write the equation for the charge, capacitance, and potential difference connection here. So we have say something like this, right? VA minus VC, the first capacitor, let's call that potential difference V1. That's Q by C1, right? VC minus VD, let's call that V2, that will be Q by C2. And VD minus VB, let's call that V3, that will be Q by C3. Let's add this. VC gets cancelled, VD gets cancelled, so VA minus VB, that's the potential in the terminals A and B, let's call that V. That will be Q. Q comes out common, as you can see here, into 1 by C1 plus 1 by C2 plus 1 by C3. So this is what we have here. Potential difference across the three of them together, that's V, and the charge, that's Q is the charge on each individual capacitor. Now we want to define equivalent capacitor. An equivalent capacitor here could be like, say, we'll replace all the three by a single capacitor. Let's call that C effective. We'll apply a potential difference, same potential difference as earlier between A and B, and if the same charge as we have here flows, well, Q has come in and Q has left that plate B because we applied the same potential difference across this equivalent capacitor. For this capacitor, you would write VA minus VB, which we called V, as Q by CE. So as you can see, this C effective is Q by V, and here say Q by V would be, say, So if you put that here, Q by C, V is Q by C, Q gets cancelled and you get 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So the effective capacitance of the three of them together is given by this equation. This capacitor can store the same amount of charge as the three of them are doing together in a series combination. Well, you can see if all the capacitors are equal, if say there are three of them C, 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 well, effective capacitance becomes 1/3 C by 3. That might surprise you. Having taken all the trouble to make the capacitance as large as possible, we are now losing out on capacitance. But then there is something else. When a capacitor is made, it has got a breakdown value for the potential difference. A capacitor cannot withstand a potential difference higher than a certain value. We've learned that earlier. So if this capacitor can withstand, say, 10 volt, you cannot apply, say, 30 volts to the combination. Say each of them withstands 10 volts. You cannot apply more than, when each to individual one, you cannot apply more than 10 volts. But put them together like this, well, the 30 volts will be shared by this as equal, 10 volt, 10 volt, 10 volt. You can see that here, the ratio of V1, V2, V3 is 1 by C1 is to 1 by C2 is to 1 by C3. So there's another thing that you can learn here. In a series capacitor connection, all capacitors will have same charge. The potential difference across the individual capacitors will be in the ratio of inverse of capacitances. That's why we're saying V1 is to V2 is to V3 is 1 by C1 is to 1 by C2 is to 1 by C3. So this is the ratio of potential differences. So we know about two things. How much charge each is, say all of them have same charge Q each. And we also have learned about potential difference. The ratio of potential difference is the ratio of inverse of capacitances. So if all the three are equal, the potential will be equal. So if you apply 30 volt here, it will be shared as 10, 10, 10, and each of the capacitors will be safe. We said each one can withstand, say, 10 volt. So in a series connection, you can apply a voltage greater than the breakdown voltage of individual capacitor for the combination. So that's an advantage. So we lose out on capacitance, but we gain in terms of the breakdown voltage. Also, this equivalent capacitance is equivalence for even the energy stored. What is the energy stored by this one? Q squared by 2C1, Q squared by 2C2, Q squared by 2C3. So energy of this system is Q squared by 2C1 plus Q squared by 2C2 plus Q squared by 2C3. So that Q squared by 2. So you can see that the energy stored is Q squared by 2C1 plus Q squared by 2C2 and so on and so forth. So if you take out that Q is common, right? So if you take out Q squared by 2, you'll have 1 by C1 plus 1 by C2 plus 1 by C3, which is 1 by C. So you have equivalence for all purposes here. Sometimes equivalence is defined with a limited purpose. So it's like this 3 can be replaced. This can be a black box. I don't know how many capacitors are in there, but if I apply a potential difference V, say a charge Q flows. So if the number of capacitors for me inside, I do not know how many there are, but if I apply a potential difference V, a charge Q flows in. That's it. So if I replace 2 of them with 3 or 4 or 5 or just 1, if same potential difference causes the same charge to be flowing in, that's equivalent. So same energy is stored, same value for the same charge on all of them. Mind you, the charge stored is not 3Q. You don't add up the charges and say it's 3Q. If you connect A and B together, well, a charge Q, this charge Q flows externally, and these two neutralize each other. So the charge stored is Q, not a combination of Q, Q, Q and Q, right? We can also connect capacitors in parallel. In this case, we'll have, say, 2 terminals, say A and B, and we have a number of capacitors between the same 2 terminals. Say, this is what we have. These are 3 capacitors. They are connected. All the left plates are connected to terminal A. All the right plates are connected to the terminal B. So all this set of plates connected to A and all this set to B. Now Well, when you apply a potential difference between A and B, you connect a cell, charge Q flows onto these left plates, and the charge leaves from that Q that flows in distributes into all the three. And for a charge leaving all these three plates will to join and then to flow through the terminal is Q. Q flows in and Q flows out. This Q flowing out, let's say, will be distributed as Q1, Q2, Q3. There will be minus Q1 here, Q1 leaves. There is minus Q2 here, Q2 leaves. There will be minus Q3 here because Q3 leaves here. So that's what we have in parallel connection. Mind you, the potential difference between the terminals A and B, if we call it V, it's same for all the three capacitors. So potential difference is common in parallel connection. Charges are different. So if you write an equation for each individual capacitor, you will get that V is Q1 by C1, also Q2 by C2, or Q3 by C3. So you can see that Q's are in the ratio of Q1 is C1 V1, say Q2 is C2 V2, Q3 is C3 V3, C3 V, sorry. So Q1, Q2, Q3s are in the ratio of, these are the two things we are interested in. Potential difference, what can I say about it? And charge, what can I about? The charge is in the ratio of capacitances. Potential difference is same for all the three of them in parallel connection. This is a branch, and in this branch you can have more than one capacitor, say two capacitors in series. Then we can know how to replace them, right? So in this case, we consider a simpler case here. Each branch has one capacitor. This is one branch. This is one branch. This is a junction. This is another junction. This is one branch, second branch, third branch. And that's it. Well, charges are in the ratio of capacitance. As potential difference is same. Now, if you want to replace this by a single capacitor, now this is what you would think of, right? So you would say, if between this same terminals A and B, if you apply a potential V and replace it by a capacitor C, the charge stored by them, this capacitor should be sum of all the three, because for how much charge is being stored here, how much is flown in through A, Q1 plus Q2 plus Q3. So for this capacitor, let's say Q is C effective into V. But what is Q? Q1 plus Q2 plus Q3. And what is Q1? C1V. So this Q1 plus Q2 plus Q3 is C effective into V. And Q1 is C1V, Q2 is C2V, Q3 is C3V. This is equal to C effective into V. So you can see C effective comes to C1 plus C2 plus C3. So capacitance is equivalent capacitance sum of the individual capacitances. So you have looks like an advantage. Your parallel connection increases the capacitance. But suppose this withstands 10 volt and this withstands 20 volt and this withstands 30 volt individually. But then when you put them in parallel, you cannot apply more than the lowest of the breakdown voltages. So it can, the system of the three can operate only at 10 volt. If you apply more than 10, they will break down. So break down in the sense the insulation part breaks down and becomes a conductor. So this no longer will store charge. That's what you mean by breakdown. Not physically breaking into pieces or something, right? So this is it. C effective is C1 plus C2 plus C3, and the Q's are in the ratio of C's, V's are same. That's what you should learn here. And energy stored, you can use well, half CV squared. So half C1V squared, half C2V squared, half C3V squared. So V is common, and the energy stored by the system is half C1V squared plus half C2V squared plus half C3V squared, right? This is the energy stored by the system, sum of the individual energies. This is electrostatic potential energy. This is V squared by 2 into C1 plus C2 plus C3, which is CE, right? So the CEV squared by 2, and that's what you would say the energy stored here is half CEV squared. So the equivalent capacitor stores an amount of charge equal to sum of the individual charges, and the energy stored by it is same as sum of the individual energy stored by the individual capacitors. So this is parallel connection.